This is your presenter Asloob Mudassar, and I am presenting slide number 130 of the course on laser physics. Question is, present the theory of active Q switching both for pulsed and continuous pumping. The answer is, let us discuss the active fast Q switching process for a 4-level laser system for which the rate equations are given by, that is dn over dt, that is the rate of change of inversion, is equal to rp pump rate minus b times phi times n minus n over tau, where tau is the lifetime of the upper state of the laser level, and d phi over dt, that is the rate of change of a photon number, is equal to va times b times n minus 1 over tau c, where tau c is the lifetime of the photon, and phi is the number of photons multiplied by the end. And both of these equations have been discussed in slide number 108, in equation number 13 and 14 in much greater detail. So you should consult these slide number 108 for the detail of these two equations, that is for equation number 1 and equation number 2. This is for a 4-level laser system. Under the pulsed operating regime, figure 129.1, that is in slide number 1, question number figure number 1, which I have reproduced in the appendix number 1. Let me show you that figure first. For example, this is the figure. You can see that the pump rate has been given and the Q switching is switched on at a time t is equal to 0. That is, the Q switch is made opened at is switched to open state at a time t is equal to 0, and you can see the pumping rate is in the form of a pulse, and then you can see that the gamma of t as a function of time has also been plotted with the two different states, with the two different constant states, and gamma c is the cavity loss when the Q switching is in the closed state, and gamma naught is the losses of the cavity when the Q switching is in the open state. And similarly, for the inversion, we have shown the plot, that is the n of t has been plotted, that is the inversion as a function of time has been plotted on the vertical side versus the time t. You can see that n of t has been labeled with the 3 categories, that is ni, which is the initial state of a population inversion just before the Q switching process, and p is the population inversion that corresponds to the peak of the photon pulse. You can see that this is the photon pulse, and if you extend this vertical line, and then the corresponding inversion is np. So np is the population inversion corresponding to the peak value of the photon pulse. Nf is the final inversion, that is when the photon pulse has completed, then the inversion corresponding to that one is nf. And here this is the plot of the phi of t. So phi of t versus time has been shown. You can see that the pulse is here. The pulse has a width of delta tau p, and the pulse occurs at a time, that time required for the pulse to reach its peak value is tau d. And the caption of the figure is time behavior of a photon pulse phi of t, time behavior of the inversion n of t, and the losses gamma of t in a Q switching under pulsed pumping technique. This equation has been discussed. You can see the label is 129.1. So this equation has been discussed in slide number 129 and in equation number 1. For much greater detail, you can consult that slide. So under the pulsed operating regime, and I have discussed use briefly figure number 1. The Q switching is performed when the inversion n as a function of time attains its maximum value ni, which can be obtained by setting dn over dt is equal to 0 and phi is equal to 0 in equation number 1. So you see that in equation number one, that is in equation number one, we can set two values. That is the rate of change of inversion is equal to 0 and phi is equal to 0. And you know that n of t attains its maximum value ni. So let me show you that value over here in the figure again. So you can see that this is the inversion, and the inversion attains its maximum value, which we call it as ni, or the initial inversion for the Q-switching process. In principle, this is the maximum value attained in the before the Q-switching process. And you know that since ni is the maximum value, it becomes flat at the top, and the derivative, that is the rate of change of d, that is the rate of change of a population inversion, that is dn over dt, can be set equal to 0 in this region, where we have attained the maximum value of the inversion equal to ni. And at that time, when the inversion is maximum, you can also see that the number of photons there is 0. So you can see that the number of photons is 0 when the inversion ni is maximum. So we can set phi is equal to 0 over here. So with these two values, that is, we can set dn is equal to, we can set dn over dt is equal to 0, and we can set phi is equal to 0, and at the same time the value of n can be set equal to ni. So if we make these changes in equation number 1, we set phi is equal to 0, and we set dn over dt equal to 0, and this n can be made equal to ni. So solving this equation for ni, we get ni is equal to tau times rp as a function of time, as at a time t is equal to 0. You see that rp at a time is equal to 0. This time which we have set at a time t is equal to 0 is actually the q, is the time when the q switching is performed, or the q switch is made opened. So this is the time. So let me show you again this time the figure. So you see that this is the time. This is the pulse repetition rate. Sorry, this is the pumping rate RP as a function of time. So you see that the pumping starts well before the Q switching process. Q switching occurs at a time t is equal to 0. So in this region, when the time is less than 0, the Q switch is closed and the pumping rate is there. You can see the pumping rate is shown, and then the pumping rate goes to 0. When the pumping rate is nearly 0, at that time the inversion has attained its maximum value equal to ni. So when the inversion attains its maximum value equal to ni, we set time t is equal to 0. You can see that we can set time t is equal to 0 there, and this is the time, this is the region, you see that, where rp is 0. But in so don't consider this rp is equal to 0 over here, but rp is equal to 0 at the time when the q switched, when the q switch is made open. So this is the time rp of t exists over here. So then we can write, solving that equation, that is the equation number 1, we can write that ni is equal to tau times rp as at time t is equal to 0. So this time t is equal to 0 is the time when the q switching is performed, that is the q switch is set in the open state. So this is the value of ni that we can determine, because tau, if tau is known, whereas tau is the lifetime of the upper state of the laser, and then rp at when the switching is performed, the value of rp if known, then you see that ni can be determined very easily. Let us assume that the time behavior or the value of the function rp as a function of time is identically the same as the pump energy ep. So under that condition, we can say that the value of the pump at the time t is equal to 0, that is at the q switching time, is proportional to ep, where ep can be determined by this value. So if you integrate the function rp, which is a function of time, with respect to time dt, that is, if you sum up all the pump rate, then of course you will get the total energy during the pumping process, which is EP. So here Rp at a time t is equal to 0, that is at the Q switching time, is proportional to the value of EP. And you know that from the previous equation, that is from equation number 3, we have the value of R of Rp at time t is equal to 0. This is equal to 0, as you can see. So we can see that Ni is proportional to Rp at the Q switching time t is equal to 0. So we have Ni, which is the proportional to Rp at time t is equal to 0, where Rp at time t is equal to 0 is also proportional to the pulse energy, is also proportional to the pulse energy. Is also proportional to the pump energy. This P subscript with E stands for the pump energy. So we can combine these two inequalities and we can write that Ni is proportional to EP. So the population inversion, the maximum value of the population inversion is proportional to the pump energy. So combining the last two inequalities, we obtain Ni is proportional to EP, that is the population inversion or the maximum value of the population inversion, or the value of the population inversion at the time of Q switching is proportional to the pump energy EP. Let us designate NIC as the initial inversion just at the threshold. So you see that this threshold value, you can see that NIC is the initial inversion just at the threshold value. Before that, we have been using only NC to stand for that. NC is the value of the inversion at the critical value of the inversion, because the C stands for the critical. Before that, we have only using the symbol NC in the previous slides, because the NC stands for the critical inversion, which is the minimum inversion required for the lasing process. And you see that here we have used I along with that one, which stands for the initial inversion, or the inversion just at the threshold value, and EPC as the corresponding pump energy. So again, EP is the pump energy and EPC is the critical pump energy or the pump energy at the threshold value. So EPC as the corresponding pump energy at the threshold laser operation, then we can write that Ni can be written as X time NIC. So the maximum value of the inversion can be written as a multiple of X to the critical value of the inversion. Similarly, the value of the EP can also be written as the value of the pump energy at the critical value multiplied by X, because this X will be the same constant of a proportionality. It is because Ni is proportional to EP. So if we write an equation with Ni and an equation for EP, then we need to put the same constant of a proportionality, which is X in our case. So Ni, which is the population maximum value of the population inversion, can be written as X times the population inversion at the critical or the threshold position. Similarly, we can write that the pump energy is equal to X times the value of the pump energy at the critical value or the pump energy at the threshold operation. So if you solve these two equations for the value of X, you can find that X is equal to Ni over NIC is equal to EP over EPC. So I have labeled two ratios, one with blue and the other with red, because I am going to explain their meanings separately. So let me explain the value of the equation with the color red. So obviously X is the amount by which the pump energy, that is EP, exceeds the critical pump energy EPC. So the amount by which EP exceeds EPC is equal to X. Similarly, now I am going to explain the meaning of this Ni over NIC is equal to X. Also, X is the amount by which the inversion exceeds the critical inversion NIC, or you can see that the maximum value of the inversion exceeds the critical value of the inversion NIC. In other words, NIC is the critical inversion when Q switching element is absent. So you see that we in one of the previous slide we have discussed that critical inversion can have two values, one in the presence of the Q switch and other in the absence of the Q switch. Here we are defining that this NIC is the critical inversion when the Q switching element is absent or the Q switch is in the open state. Thus we can write that NIC is equal to NC is equal to gamma over sigma L. You see that this relation that NIC, that the critical inversion is equal to gamma over sigma times L. This is what we have been writing in many of the previous slides. Now here we are now writing with our current notation that NIC is equal to NC is equal to gamma over sigma into L, where again NIC is the critical value of inversion. So here we can say that when we say that the Q switch is in the open state, it means you can assume that the Q switching is not the Q switch is not present. And when we say that the Q switch is in the closed state, it means that the Q switch element is present. So this is what the critical inversion that we have defined, and we have linked over NIC parameter with the previous parameter NC, that is the critical inversion is equal to gamma over sigma into L, where gamma is the critical loss and L is the length of the laser medium. And sigma is the absorption cross section of the laser medium. This could be the stimulated absorption cross section. All these are measured when Q switching element is absent or open. So you see that we can measure these parameters, that we can measure gamma, we can measure sigma, we can measure L, and this measurement should require that the Q switching element is absent or the Q switching element is open. Assuming that EP and EPC are known. So you see that we are assuming that both are known. That is the pump energy, that is the maximum value of the pump energy, that is the value of the pump energy that is equal to the, has been related with the pump energy at the critical value as in the previous equation over here. So if here we are assuming that EP is known and EPC is also known, so it means that X is known. So assuming that EP and EPC are known and that gamma, L and sigma are also known. So from equation number 7, we are also assuming that gamma is known, sigma is known and L is known. So NIC, that is the critical value of inversion, is also known. Then Ni can be calculated using this equation. That is from equation number 6, we have this one. So Ni can be calculated because NIC shown in green is known, X is also known because EP and EPC are known. Their ratio determines the value of X. So X is also known, NIC is also known through this equation because gamma is known, sigma is known, L is known. So NIC is known, and due to that one, this Ni is also known. So the value of the the value of the maximum value of the inversion or the value of the inversion just before the Q switching process or at the time the Q switch is made on is known. So Ni is the inversion at which the Q switch is made in the open state. The time evolution of the system after Q switching, that is the time greater than 0, is performed. The time evolution of the system after the Q switching, and you know that after the Q switching occurs at a time is t is equal to 0. And when we say that the time evolution of the system after Q switching, it means that the time evolution of the system at a time t greater than 0 is performed, can be obtained using equation number 1 and equation number 2 using the conditions. So you see that now we are looking for to determine the system evolution for the time after the quiz switching, that is at the time t greater than 0. It means that we want to use equation 1 and 2 to come out with such a condition, with such a time evolution. And we are using the condition, that is the population inversion at the q switching time, that is at time t is equal to 0, is equal to ni, that is the maximum value of inversion. So let me show you again in the figure. You can see over here, this is the maximum value of inversion, and this is the inversion that also corresponds to time t is equal to 0 when the q switching is performed. So you can see that this is the time. And when we say that the q switching is formed, that which means that the q switch is set to be in the open state. And n of t, that is this value of n, that is the inversion at the q switching time t is equal to 0, is equal to ni. So we are using the conditions at the q switching, that is n at a time t is equal to 0 is equal to ni, and the number of photon when the q switching is just started, that is at a time t is equal to 0, phi is equal to the initial value of the number of photons, and we are assuming that initially at least one photon is present in the cavity. And you can also see this one from the figure. So you can see that this vertical line corresponds to time t is equal to 0, and at a time t is equal to the pulse just started. It means that we can assume that the phi of t, phi at a time t is equal to 0, is equal to the value of the photon which is present initially. And here we are assuming that the initial value of the number of photons in the cavity just at the start of the q switching is 0. Okay. So this is the second condition. So under these conditions, that is inversion at a time t is equal to 0 equal to ni, and the photon number at the time is t is equal to 0 is equal to phi I is equal to phi. Here we are talking about time t is equal to 0 is the time at which the q switch is made open, that is set in the open state. After the q switch, after the q switching, the time evolution of the system, you know that the time evolutions of the system is determined by these two parameters, that is n as a function of time, inversion as a function of time, and the number of photons as a function of time. These two parameters will determine the state of the system or the time evolution of the system. So after the q switching, the time evolution of the system takes place on a very short time scale, such that rp, that is the pump rate, and n of n divided by tau, that is the decay of a population inversion through the spontaneous emission, can be neglected. So we can neglect these two because our time scale for the q switching is very fast, and rp and n over tau cannot respond in such a fast at such a fast pace, and we can regard these two quantities to be equal to 0, and we can neglect them. So if we neglect these two quantities in equation number 1, for example, this equation, so if you neglect rp and if you neglect this term n over tau, you are left with this middle term only. And all the terms in equation number 2 will survive for that one. So we have written these two equations as, so this is equation number 8, which is dn over dt is equal to minus b times phi times n, and d phi over dt is equal to this. Within the parentheses, we have va times b times n minus 1 over tau c times phi. So the second equation remains unchanged, whereas in the first equation, the first term and the third term on the right hand side of equation number 1 were neglected, and then we wrote down from equation number 1. This equation was written under these two conditions, that at the time of Q switching, that is at the time t is equal to 0, the population inversion at time t is equal to was equal to Ni, that is the maximum value of inversion, and the number of photons at a time t is equal to 0 was nearly equal to 0, because initially we are assuming that only one photon was present. So we have these two equations. So these two equations will help us to develop the time evolution of the system. That is, we can solve these two equations for the value of n as a function of time and phi as a function of time. So this will give you the time evolution of the system. And time evolution of the system means that we want to see that what happens to the system and after the Q switching process. That is at the time that t is equal to 0 is set, and then we have these two equations over here. In figure number 1, which I have discussed in the appendix, the inversion NP corresponds to the peak value of the photon pulse, where d phi over dt can be set equal to 0. So let me show you in the figure again. So you see that from this one you can see that is the number of a photon, that is the photon pulse is created when the inversion falls, the photon pulse is created, and at the maximum, at the peak value of a photon, the population inversion is actually NP. So NP is the population which corresponds to the peak value of the photon pulse. And you know that at the peak value of the photon pulse, you can say that the curve becomes flat and parallel to the time axis. We can say that the derivative of d phi over dt can be set equal to 0. So d phi over dt can be set equal to 0 for this pulse at its peak value, where the population inversion n or n as a function of time becomes equal to np. So if you set d phi over dt is equal to 0 in equation number 9, that is in this equation, if you set d phi over dt is equal to 0 and solve this equation for the value of np, you know that when you set d phi over dt is equal to 0 in this equation, you need to set this n, which is a function, which is n of t, that is a population as a function of time. This should be equal to, this should be set equal to np. So setting this n equal to np and setting d phi over dt is equal to 0 and solving this equation for the value of np, you can find out this expression. That is the population inversion corresponding to the peak value of the photon pulse is equal to 1 over Va times B times tau c. And if you solve this equation for the value of B, then it becomes, I am not going to solve this equation for the value of B, but from equation number, from slide number 108 and equation number 10, which I am reproducing over here. So from equation number, from slide number 8, equation number 10, I have the relation that B is equal to sigma into C into L divided by VA divided by LE, where LE is the effective lifetime, E is the effective length of the cavity, and VA is the volume of the active medium rod. Sigma is the sigma has been defined earlier, and C is the velocity of light, L is the length of the active medium rod. And you know that also from the same slide, that is from slide number 108 and equation number 12, you have the time tau c, which gives you the lifetime of the photon in the cavity. So the value of tau c from equation number 12 is equal to tau c is equal to Le over gamma c. So you can put the value of B into equation number 10. You can put the value of tau c in equation number 10. And then the final expression for the value of NP comes out to be equal to this, as shown in equation number 11. That is NP is equal to 1 over, which is 1 over, which was 1 over VA times B times tau c, substituting the value of B and tau c and simplifying the result. We have this result equal to gamma over sigma times L. And you know that this gamma over sigma times L, as mentioned earlier, is equal to NC, which is the critical value of inversion. And we have set that value also equal to NIC. So NP, which is the maximum, which is the value of the inversion corresponding to the peak value of the pulse, we have found this one in equation number 1, that this is actually equal to the critical value of inversion, NC or NIC. So it means that NP, which we are labeling in our previous slides, that NP is actually the number of inversion corresponding to the peak value of the photon plus. This is actually the value that is also the same as the critical value of the inversion. Now you see that we have this relationship over here from equation number 6, that Ni over Np is equal to X. Let me show you equation number 6 first. This is the equation number 6. And you know that in equation number 6, you have a parameter Ni over Nic. That is the critical inversion is dividing Ni. So here we can replace Nic with the corresponding value Np. Because here we have obtained the relation, that is we have obtained the relation that NIC is actually NP. So we can replace NIC in equation number 6 by the value NP, and we have this relationship that NI divided by NP is equal to X. And you know that you must remember that now the value of NP is known, which is equal to the critical value of the inversion. And you know that X is also known. So it means that NI can also be computed. The peak value in the output power pulse is given by. So you see that now we are going to calculate the peak value in the pulse. So where is the pulse? Let me show you the pulse. The photon pulse. This is the photon pulse in equation number, in figure number 1. This is the photon pulse. So can we calculate the value of the peak power? Because this is the pulse that will be transmitted out from the laser beam. And if you want to calculate what is the peak power in that pulse, you can find out the peak value, which I am going to calculate. So this is the value of the peak power. O stands for output, peak, P stands for power. So the two subscripts are defined as the output peak, and this capital P is defined as the power. So output peak power from the laser output will be given as gamma 2 times C over 2 LE times H nu times phi P. Since we are calculating the peak value corresponding to the output pulse, we are using the photon flux, which is present, which is corresponding to the peak value of the number of photons. So this phi p is actually the photon number corresponding to the peak, and that is why this is the corresponding peak value, peak output value from the laser output beam. So this is the peak power, output power from the laser beam, and gamma 2, you know, that is the loss due to the output mirror, and the rest of the quantities have been defined, and this is the formula we have also used before many times earlier in some previous slides, where phi p is the photon number corresponding to the peak of the pulse. To find phi p, we divide equation number 9 by equation number 8 and introduce np using equation number 10, which gives. So we have equation number 9. This is equation number 9. We divide both sides of this equation number 9 by the both sides of by equation number 8. So dividing equation number 9 by equation number 8 and introducing equation number 10. And after introducing equation number 10, we have this equation, that is d phi over dn, that is the rate of change of photon flux with inversion, is equal to minus Va times 1 minus Np over N. The solution of this equation is given as, so I am not going to produce, I am not going you to going to give you the detail of this solution, but the solution you can find this solution to be equal to this, that is phi is equal to, or you can say that phi of t is equal to VA, and within the square bracket we have Ni. Ni is a, you know, that is a constant number, maximum value of the inversion, minus n. This n is actually the function of time. So this n is a function of time. You can say that this n of t minus np. So np is the maximum value. So np is the value of the inversion corresponding to the pulse peak. You can also write this as the critical inversion and multiplied by the log of ni over n. So here n, capital N, is actually the function of time, and this phi is also a function of time. So in writing this equation, we have neglected the value of phi I, because the value of phi I is very small. You can ignore the contribution of this phi I, and you can set n is equal to np. When we set n is equal to np, the photon peak occurs. You know that the population inversion at the photon peak is given by np. So this is the population inversion. So you can set this population inversion to be equal to np when you set phi is equal to phi p. So on the left hand side, this phi will be replaced by the maximum value of the photon, number of photons at the peak value, which is phi p. And here equivalently, you can set n, capital N, equal to np. So you see that this is the relation now we have obtained for the number of photons at its peak value. So phi p is equal to Va times np, and within the square bracket we have Ni over Np minus log of Ni over Np minus 1. The elements, the terms which I have shown in green, these are the terms which are known. So already known quantities are shown in green. And of course, this Va is already known because it is the laser parameter. But you know that these are the parameters of the systems, and these parameters in green have been shown in green, and these parameters are known because we have discussed that how we can find out these parameters in the previous pages. So the number of so the maximum value of the photon, that is phi p, maximum number of photons at the peak value phi p, is known. So when this value is known, you can substitute that value over there, and you can find out an expression for the peak output power from the laser beam. So in equation number 14, that is in this equation, Np is known through equation number 10, and Ni over Np is known through equation number 12. So these equations are, through these equations, we know the parameters. We know Ni over Np, we also know the value of Np. And Va is, of course, is the parameter of the cavity, is also known. So it means that phi p is known. Now let's to find out some meaningful results. We can also write log of Ni over Np in some more appropriate form. Okay, so let's first of all solve this one. Va times Np. This is Va times Np, and you know that this is equal to 1 over B times tau c. That is from equation number 10. You can see from equation number 10, you can write this one, that is Va times Np is equal to 1 over B times tau c. The value of B is also calculated earlier, and you can substitute the value of B by this value, that is Va times Le over sigma into C into L. And then you can rearrange the term, that is AB can be written. What is AB? AB is the cross-sectional area of the active medium rod, and that is equal to VA divided by L. That is the volume of the active medium rod divided by the length of the rod will give you the cross-sectional area of the rod, which is AB. And I have VA divided by L can be written as AB divided by sigma, and then the rest of the terms are LE over C times tau C. And then you can rearrange these two terms, in the form of the product of these three parentheses. The first parenthesis contains AB over sigma. The second parenthesis contains LE over C. The third parenthesis is 1 over tau C. Thus, from equation number 14, this is equation number 14. So, from equation number 14 can be written in the form in this form by replacing V8 times NP by the product of these three parentheses, which is reproduced over here. So, using equation number 13, we can also write down this equation, that is LE over LC can be replaced by. So let me show you equation number 13. So this is the full expression for the number of photons at the pulse peak. And you see that this phi p can be substituted over here. In equation number 13, phi p can be substituted over here, and we can find out the final expression, which give you the peak output power from the laser, as given in equation number 16. So you see that now we have found the peak output power from the laser, which is given by this term on the right hand side. The first parenthesis is gamma 2 over 2. The second parenthesis is AB over sigma. The third parenthesis is H nu over tau C. And the rest of the quantity is this one. This value of LE over sigma was cancelled out because this is already this expression, this LE over C is present already in equation number 13. So we have obtained the final result for the output, for the peak output power from the laser beam corresponding to the peak value of the photon pulse. So the output pulse energy expression is now given by. So E of t, if you now calculate the energy, so you see that whenever we are talking about the pulse energy, it is preferable to calculate the energy of the pulse. So the output pulse energy expression is given by E of E as a function of time is equal to the integral from 0 to infinity, and you are summing up the output power as a function of time. So P of P out, that is the power out as a function of time integrated with respect to dt. Now you see that we are talking about the output power as a function of time. This was the expression was the peak value of the output power. Now we don't want the peak value, we want the expression of power output power as a function of time. And this is what we can obtain from this equation. That is from this equation. So you can replace left hand side by just only PO. That is the PO as a function of time can only be obtained when you replace this phi p by the function phi as a function of time. So then the output power P out as a function of time is given by this expression that I have shown you just a minute ago, and then the integral will be around the value of this one, that is phi of t with respect to dt, integration from 0 to infinity. It means that we are going to sum up all the number of photons present in the pulse. So let me show you the pulse again. So this is the photon pulse, and we are going to integrate all the number of photons present in the pulse. So then we can calculate the total energy available in the pulse. And you see that this is given by equation number 17. But you know that we have to evaluate the value of this expression, that is the integral of phi of t dt. To evaluate this integral, we arrange equation number 9 in the following form. Because in equation number 9, we have phi of t. So let me show you equation number 9 again. So this is equation number 9. And you know that in equation number 9, phi of t is present. So this is the derivative of a phi of t with respect to time. and here phi is present in the form of a phi of t, and we can write down this equation number 9 in the following form. So in that equation, we have multiplied both sides of equation number 9 by tau c and also by dt, and we have rearranged the term. So after multiplication with the tau c on both sides and by dt on both sides, we have tau c times d phi is equal to Va times tau c times b times phi times n times dt minus phi times dt. So this is now our equation number 5 in the rearrangement, in the rearranged form. Now we are going to integrate all the terms from 0 to infinity, because we want to find out the value of this expression. It means that we need to evaluate this expression and we need to evaluate this expression. Once these two expressions are evaluated, we shall substitute the values of these two expressions and then we can find out this expression. So let me calculate this one first of all. This integral from 0 to infinity and d phi. So if you integrate this one, you will get the value of phi and apply the limits. The first limit will give you phi at an infinity and minus the phi at initial time. You see that the pulse vanishes at large time. So we have zero number of photons, and we have the pulse which is just started at the beginning. The number of photons was initially zero. So we can say that 0 minus 0 is equal to 0. So this integral contributes 0. Now let's evaluate this integral, the middle integral. And in the middle integral, we have integral from 0 to infinity b times phi times n times dt. From here, you see, this is what I have copied over here. And then I am going to integrate this one. But you know that this is equal to dn minus dn, as you can see from equation number 8. So let me show you equation number 8 also. For example, this one. So you can replace minus d times phi times n times dt by the value equal to minus dn. So I have replaced that one by minus dn over here. This is the minus dn. And if you solve this one, at infinity, the inversion value is equal to final value of inversion nf. And at time t is equal to 0, when the q is switched, when the q switching is started, that at a time t is equal to 0, the inversion that was present was equal to ni. So we have minus times within the parentheses, we have nf minus ni, which can be written as ni minus nf. So you see that now the two integrals have been that is, this integral is equal to 0 and this middle integral has a value equal to ni minus nf. So substituting the value of these two integrals and rearranging the terms, you have the value of phi of dt, phi of t with respect to dt, the integral from 0 to infinity will give you a value Va times tau c times ni minus nf. So you see that now you can use this value over here in equation number 17, because in order to find the energy of the pulse, you wanted to calculate this integral, and now we have this integral. So substituting the value of this integral over here, the value of the energy in the pulse is given by this expression. So you can see that these are the expressions, and now I have the terms. This gamma was cancelled out with the values of c into tau c over Le. So this was cancelled out by that one, and the rest of the terms are and the rest of the c into c tau c and Le have been combined into the value of gamma. So now we have gamma 2 over 2 gamma times Va into h nu times Ni minus Nf. So this is the energy of of the pulse as a function of time. Where we have used this expression for the gamma, that is c times tau c over Le is equal to 1 over gamma. Now let us interpret equation number 19. That is this equation. So let us interpret equation number 19. Ni minus nf is the available inversion, because after the nf the inversion is nearly zero, and before the ni the inversion is not present, because the maximum value of the inversion is ni. So ni minus nf is the available inversion. And if you multiply it with Va, where Va is the volume of the active medium rod, times Ni minus Nf is the available photons, because each population inversion species will give you one photon when the population decays. So multiplying with Va will give you the available number of photons, and gamma 2 over 2 gamma is the fraction of the total photon that contributes at the output energy. And you know that gamma 2 is the losses due to the output mirror, and gamma is the total loss. So this is the ratio of the two losses, and we can say that this gives you the fraction of the photon that contributes as output energy. The final inversion NF in equation number 19 is still unknown. So you see that in final inversion NF is still unknown in this equation. So NF in equation number 19 is still unknown. Let me show you the figure first. You see that in figure we have found the value of Ni, we have found the value of Np, but still Nf is still to be found. So let's see that how we can find the value of Nf. So we have now to determine the value of Nf. Once the value of Nf is known, then the whole expression for the energy in the pulse as a function of time would be known. To find Nf, we set t goes to infinity in the equation. You see that this equation we have already worked out, and this gives you the number of photons as a function of time. This n is also a function of time. This n in the denominator is also a function of time. Here phi is also a function of time. So when the time is very large, then of course the pulse has vanished. That is, the number of photons will be zero. So let's set the time. T is equal to infinity. So here phi as a function as a phi when the time is infinity is equal to Va. Within the square bracket we have Ni minus n at the time of infinity, and similarly this n at a time infinity. And you know that when we have the infinity time, then of course the population inversion at infinity will be replaced by the value Nf. So I have replaced n as a function of n at infinity to be equal to Nf. Again, this n at infinity has been replaced by Nf, and this phi, that is the number of photon at infinity, has been replaced by 0. And of course, solving this equation, we have Ni minus Nf is equal to Np into log of Ni over Nf. And dividing both sides by Ni, I have Ni minus Nf divided by Ni is equal to Np over Ni into log of Ni over Nf. So you see that here I have a term log of Ni over Nf. Let's express the logarithmic part in the following form. So log of Ni over Nf can be written as this, because we can move Ni in the denominator in this form, and we can add Ni and also can subtract Ni in the denominator, and then you can divide Ni only on this term and also on this term, and then we have 1 over 1 minus log of 1 over 1 minus Ni minus Nf divided by Ni. So this is a simple mathematics. And now we can introduce Ni minus Nf divided by Ni by a quantity which is eta times E. So this has been defined, that is Ni minus Nf divided by Ni has been defined as eta E. Where eta E, so this is where we define eta E as the inversion utilization factor, inversion utilization factor, or equivalently the energy utilization factor. That's why the subscript E has been used in order to make it to stand as the energy utilization factor. And in principle, it is also the same thing as inversion utilization factor. So equation number 20 now can be expressed as, this is equation number 20. So now you can represent, now you can substitute the value of logarithmic value of ni over nf from the expression, and also can introduce the eta e there, and then the final expression for the eta e becomes eta e is equal to np over ni into log of 1 over 1 minus eta e, and then rearranging the logarithmic part, we have a minus np over ni into log of 1 minus eta e. So you see that now you can introduce the value of this eta e in equation number 19. So this is equation number 19 over here. So you see that you can introduce eta. If you divide ni minus nf divided by ni and also multiply this equation by ni, so dividing and multiplying the right hand side of this equation by ni and introducing the value of eta e, you get this expression of the energy. That is the pulse energy as a function of time is equal to this expression. And here I have introduced L in the numerator as well as in the denominator, so that I can write the energy in our desired form. That is E, that is the pulse energy as a function of time is equal to this function. And I have introduced sigma in the numerator as well as in the denominator, so that I can rewrite this expression as this. So you see that gamma 2 over gamma 2 divided by 2 is the same. AB over sigma is also the same, and the sigma L over gamma has been replaced by 1 over NP, and then we have H nu, and then multiplied by Ni into eta E. And similarly, you can rearrange these terms, that you can combine these two parentheses. So gamma 2 by 2 times Ni over Np. So now I am combining the population inversion terms. So Ni divided by Np has been combined, and then we are left with eta E, and then AB over sigma, and then H nu. So this is the final expression that we have written down. On the left hand side, we have the energy of the pulse as a function of time, and on the right hand side we have the given parameters, and all the parameters in equation number 22 are now known to us. So we can determine the value of the function, we can determine the value of the pulse energy as a function of time using equation number 22. Now the width of the output pulse is defined by, again let me show you the pulse. Delta tau p is the width of the pulse. Can we find this one? Yes, we can find this one. For this one, we require two things. One is the energy function, that is the energy function of this time, which we have just found, that is E as a function of time. And the second value is the peak output power. We have also found that one. So we can find out delta P very easily because we have already calculated the relevant quantities. So over here, so delta tau p is equal to the pulse energy as a function of time divided by the peak output power of the pulse. And we have these two expressions with us. Using E of t from equation number 22 and P pulse and the output peak pulse power from equation number 16 are available. We can substitute these values, and then delta tau p, that is the pulse width, is given by this one. So this is the width of the pulse of the output pulse, and it is determined by the right hand side quantities. So all these quantities on the right hand side are also known. where Ni over P is equal to X. Because X, you know, that is already known. So this ratio is also known. So you see that in the numerator, you have Ni over Np. You can write X instead. So X into eta E divided by X minus log of X minus 1. Because X is equal to Ni over Np. Thus, delta tau P can be determined as a multiplicative factor of eta E. So here eta is present and the rest of the quantities were constant. So you can write that delta tau P is actually a multiplicative constant of the factor eta E. Now what is tau D? Tau D is the time at which the pulse peak occurs after Q switching. So let me show you tau D in the diagram. So this is tau D, you see. So this is the time at which the pulse peak occurs after the Q switching process is set in the on state. So now the parameters tau D is to be determined. So tau D is the time at which the pulse peak occurs after the Q switching process. This time can be determined by using the approximation that, so these approximations are very sensitive, be careful to understand them. That is the inversion as a function of time is approximately equal to Ni is still valid even when the number of photons in the peak are decreased by 10 times. So if the number of photons are even in the peak are decreased by 10, even then we can approximate over population inversion as a function of time by the fixed value Ni. So we are using this and using equation number 10, equation number 12, using equation number 10 into using equation number 10 and equation number 12 into equation number 9, and in the presence of that is n as a function of time, that is the population inversion as a function time, to be substituted by the value Ni, the solution of equation number 9 is given by. So let me show you equation number 10, equation number 12 and equation number 9. So you can see that this is equation number 9 which we are going to solve. And here n, you see that n is present. We are replacing this n of t by the value Ni. We can use equation number 10 in order to represent the relevant parameters. Equation number 12. We can use equation number 12. We can use equation number 10. We can use equation number 12. And we can put these values in equation number 9. And we can solve equation number 9, which gives the following result. This is the result. So phi as a function of time is equal to phi I, that is the initial value of the number of photons, multiplied by e to the power x minus 1 multiplied by time divided by tau c. So this is the expression that we have obtained for the value of photons. And now you see that this value, for this value we have in order, you see that we have made this expression, that is population inversion as a function of time. This quantity, which was a time dependent, we have replaced this quantity by a fixed number, that is Ni. Under the condition that is the number of photons at the peak value when divided by 10, even then this holds, that is we can replace phi also by a fixed number, that is phi of, that is the number of photons present in the peak divided by 10 can be used for the value of phi. So now we are using these parameters. Initial value of number of photons is equal to 1. We are using phi is equal to phi p divided by 10. So this phi will be replaced by the phi pi divided by 10, and this t will be replaced by tau d. Because when t will be replaced by tau t, we have solved this relationship under the condition that phi can be set equal to phi p divided by 10, and the value of n of t, which is a function of time, can be set equal to a fixed value ni. Under these two conditions, we have solved equation number 9, and we have obtained this solution. Now in this solution, we are going to replace phi by the value of phi p divided by 10, and this time now corresponds to the time equal to tau d. So making these substitutions, we can solve equation number 24 for the value of tau d to be equal to tau c divided by x minus 1 into log of a phi p over 10. So you see that tau c is known, x is known, phi p is known. So it means that all the quantities on the right hand side are known. So it means that tau d is known. So you see that it has been noticed that even if you replace this phi p in the denominator, if you replace 10 by 20, even then the value of tau d is not changed significantly. So even that phi is equal to phi p divided by 10 can also be used as far as the practical situation is concerned. So phi p is usually very large. It is found that choosing phi is equal to phi p divided by 20 in equation number 25 does not change tau d much. And this change is negligible for practical purposes. For the continuous pump mode operation, we refer equation number 2. For continuous pump mode operation, we refer figure question number 129.2. So let me show you this figure first. This is given in appendix number 2. You can see that the pump rate is continuous and constant. As a function of time, it is constant. And you can see that the losses fluctuates. So losses becomes lower when the Q switch is on, and when the Q switch is in the off state, that is in the closed form, then we have the maximum losses equal to gamma C. Otherwise, when the Q switch is open, we have the losses equal to gamma naught or gamma O. You can see that the population inversion much similar to that of the pulsed pump rate case, and you can see that a number of pulses are emitted. These are pulses, they are emitted at the same time in the same configuration as we have discussed for the pulsed case, for the pulsed pump rate case. And you can see that tau p is the time between the two pulses, between two consecutive pulses. And this is the time behavior of a photon pulse phi of t, inversion n of t, and losses gamma of t in a Q switching under continuous pumping scheme. This figure has also been discussed in slide number 129 in much greater detail. You should consult the detail of this figure. You should consult slide number 129. So for the continuous pump mode operation, we refer figure number 2 of slide number 129, where the Q switching pulses occur periodically. The process of inversion building and formation of pulse after Q switching are still governed by the rate equations given in equation number 1 and equation number 2 of the current presentation. Some quantities like peak power as given in equation number 16, output energy as given in equation number 22, and pulse duration as given in equation number 23 will stay the same even for continuous pump mode operation. The equation Ni over Np is equal to 0 is not valid. However, because after each Q switched operation, After each Q switched pulse, the inversion may attain a different Ni, starting from the same or the different final inversion Nf. The inversion must attain a peak value before tau p, which is the time between two consecutive peaks. The inversion changes from Ni to Nf in a time tau p, and the pulse vanishes, that is phi becomes equal to 0 after tau p. With these conditions, the solution of equation number 1 gives you. So you see that solving equation number 1 will give you this result. I am not going into the detail of this one, but under the given conditions as explained over here, you can use those conditions and you can find out the solution of that equation in the form of this one. So we have Ni is equal to Rp time tau minus, within the parentheses we have Rp tau minus Nf, outside that parenthesis we have e to the power minus tau p over tau. And you can also split the parenthesis, and you can write down in the two form, that is Ni is equal to Rp times tau multiplied by 1 minus e to the power minus tau p over tau plus Nf times e to the power minus tau p over tau. So you see that this is what we have written for the continuous case, the value of Ni. Because here we have stated that Ni over Np is equal to x is not valid. So we are now going to investigate the value of Ni, which we can find using the continuous case like this. And you see that here tau p, which is the pulse repetition time, is also involved in the calculations of Ni. To express this equation in a more intuitive form, we introduce x is equal to Rp over Rcp, where Rp is the pump rate at time t and Rcp is the critical pump rate, where the critical pump rate have been found in many of the previous slides as given, that the critical pump rate Rcp is equal to Nc, the critical population, divided by the time tau is equal to Np divided by tau, because Np is equal to Nc, and that is equal to again Rp over tau. Because you can find out the value of Rcp from this expression, that Rcp is equal to Rp over x. So you see that you can use the value of x is equal to x. For example, from here you can find out the value of x, and you can substitute the value of x in the previous equation in the form of Np over tau, and you get this equation 27. So you see that Ni over Np is equal to x. This was unknown, you see. So we have found an expression for that one. That is x times Np over Ni. Within the square bracket, we have 1 minus e to the power minus 1 over f star is equal to 1 minus Nf over Ni multiplied by e to the power minus 1 over f star. From x, which is equal to Rp over Rcp, it follows that x is the amount by which the continuous pumping exceeds the threshold pump value. And f star is equal to, we have written f star over here in equation number 27, whereas f star is equal to tau times f is equal to tau times over 1 over tau p, because f is equal to 1 over tau p. Here f is the frequency of the pulses and 1 over tau p is the separation between the pulses, where f is the repetition frequency of the pulses. If x and f star are known, Np over Ni and Nf over Ni can be computed. The energy utilization factor can thus be obtained, that is eta E is equal to minus Np over Ni multiplied by the log of 1 minus eta E. So you see that we have explained the pulsed case in a much greater detail, but we have not given the same detail for the continuous case. But because most of the things will be similar as that of the pulsed case, the only difference was that Ni over Np is equal to x was not valid, and here we have explained the expression or how we can obtain the expression of the Ni, and then we have also obtained a solution over here that can relate the required quantities, and we can find out these quantities because if x and if x and f star are known, it means that we can find out the other quantities also. Even we can also find the energy utilization factor for the continuous pump rate case. And we included in appendix 1 figure number 1 from slide number 129 for the, which is valid for the pulsed case, pulsed pump pulse, and for the continuous pump rate, which is constant with the time. We have also discussed the mechanism from using figure number 2 from the previous slides. So this is the end of slide number 130.